Our webinar today is about our path-equipped Nozzle-FEM software. First, just 1 minute about our company. So, Path Suite software is not something new in the market. In fact, it has more than 50 years history and have more than 3,000 active users worldwide. But it wasn't in the world market. It was mainly on former Soviet Union and Russian. And then about 5 years ago, we start also to come to world market. And so now we're prepared with practically all international standards and also have users in many countries. So we try to combine best-in-class modern methods and algorithms and libraries with embedded software and support with industry experts, and try to deliver you very user-friendly and flexible tools on affordable price and flexible licensing. So here is just a small portion of our users. You can see there some famous names, like maybe you know, Technip, FEMS, Mitsubishi, Technical Leonidas, Skoda, and so on. So now about this specific software. Why do you need Nozzle-FEM and who needs this software? This software is on the boundary between pressure vessels design and analysis and piping design and analysis. Because always you have some, in any piping, and especially in process piping, you always have some kind of nozzle junctions between vessel shells or heads and piping. So there is a permanent dispute between pumping designers and vessel manufacturers. What are allowable loads on the nozzle? And of course, piping designers always want to increase these loads, and vessel manufacturers try to decrease them. So we need to calculate it. And in order to calculate it, we also need, and we need to calculate it if this nozzle-shell junction is fit some requirement conditions. To do this, we need some loads from piping, from attached piping. And to calculate these loads of attached piping, we need to model this in some pipe stress analysis system. And to model it correctly, we also need to know some flexibility parameters of this junction. Because if you will model it just by anchor support, it was too much conservative approach. And you will get not very good results, not really realistic results. So you need to solve two tasks. You need to check your strength of your nozzle junction, and you need also to get stiffness and flexibility of nozzle junction to use it in your piping stress analysis calculations. So how to do this? There are several approaches. There is analytical approach according to some industry standards like WRC, different variants of WRC. There is, you can use also some universal solvers like ANSYS, Nastran, etc. And you can use some special software like our path-equipped Nozzle-FEM. So many of you, of course, know and use this WRC standards. And of course, we have it in our software, both in piping analysis and in vessel analysis, but this approach is very restricted and have a number of disadvantages. It covers a very small number of typical geometries, mainly cylindrical and elliptical shells, only radial nozzles. And of course, it provides quite conservative results. Okay, you always can use some universal solvers, FEM solvers like ANSYS. But to do this, you need a lot of work and you need to be expert, because you need to create your geometrical model, you need to create finite element model, and you need to handle calculation results yourself. And usually you cannot do this every day. And usually this type of calculations you need to do very often. Not to say that this software is, of course, quite expensive. And specialized software. This specialized software is special software which just focus on solving this specific task. It will solve it with finite element method, but it will do everything itself. So you don't need any special knowledge or skill. It will save you time. It will provide accurate results, and it will cover a wide variety of shell and nozzle configurations. All you will need, just enter your data and press a button and get your results. So what is main features of Nozzle-FEM? So it can calculate stress and flexibility of nozzle shell junctions, and not only junctions, but also some other elements like teeth, non-standard teeth, schizophores, and we are going to increase this list of elements. Of course, it can calculate allowable loads. It can calculate the stress intensification factors, and under different loads combination, including pressure hydrostatic and temperature loads, and so on. It can do also fatigue analysis, and of course, we also include analytical calculations according WRC. So let's look at in more details about Nozzle-FEM capabilities. Oops. So this is like the window of the program looks like. So you have 4 tabs, and you just need to, what you need to do to make these calculations. First, you need to select attachment element type. So what kind of connection of junction you are going to calculate. Second, you need to select your national or international code for stress analysis. You also can choose some additional calculations like calculating loads, calculating stiffness or flexibilities, stress intensification factor, or also some analytical methods like WRC. And of course, you need to set some parameters to control calculation accuracy. But of course, these parameters also are set by default. So let's go to these items. First, supported codes. So we have all kinds of widely used codes in the software. This includes ISME, Division 1 and Division 2, latest standards, or also European standards, Chinese standards, and all parts of Russian standards for linear elasticity, for load cycling loads, and also in corrosion hydrogen sulfide medium. Oops. Just a moment. Yes. Now about accuracy of results. This is a delicate question because you know that, of course, your results will, to some extent, depend of your mesh. So how good is your mesh? So the software created the mesh itself. But of course, it's natural that you can do very refining, very good mesh, and will have a very long time of calculation. Or you can just get quite not so good quality mesh. The calculation will be very fast, but results can be doubtful. So how to solve this? So we set 5 levels of mesh. And we also made, and this mesh is, you see, it's different. It's more good in the vicinity of some edge. And we also made a lot of numerical tests and look how for different level of mesh and different types of loads, the stress, what is the accuracy of the stresses. And so we defined some kind of safety factor. It's a stress factor Km. And this can say, this is, for example, how the stress factor looks for one of the type of the loads. And this safety factor is taken into account automatically by program. So if you just have first level, you can very quickly make the estimation. And if the program said that everything okay, so you can just take these results and don't worry about this. In some case, of course, you will need to set more second or more levels of mesh. Wait a bit and make more accurate calculations. Another point is convenience of results. Along, besides the mesh, we use this so-named hotspot stress method. This method allows to take into account the change of stress near the vicinity of well-toe, because you know that theoretically the stress in this geometry can be infinite, but of course this is not physically realistic, and there is a known method which is allows to calculate stress by a linear extrapolation of 2 points. So this is, sorry, yes, the articles about this method, it's known internationally. So we also implement it and all estimation according to hotspot stress method is done automatically. This is just a small example. So you see the upper 2 pictures showed as what will be results with extrapolation, and so on the first level of mesh, you will not get good results. You can have too small stresses. And on the second level, you see the results practically independent of the level of the mesh. Okay, now about geometry. So what kind of shell elements are included? So practically all kinds of shells. So it's cylindrical shells, conical shells, shallow storage tank, also conical reducer, and different kinds of heats, including hemispherical, toruspherical dish heat, elliptical heat, and flat surface, including even rectangular plate. Another interesting thing that you can also set shell orientation. It is important for hydrostatic to take into account hydrostatic pressure and how it changes along the shell. So the program can automatically calculate additional hydrostatic pressure for horizontal position or for vertical position, or you can invert vertical position. So bottom heat or top heat. Type of nozzles. So you can consider different type of nozzles, including cross sections. Right? You can set different type of reinforcements, junction types, and nozzle placement parameters. So you can have nozzles with reinforcing parts, with nozzle inserts, with barrels, with tuning connections, junction in pipeline, and also with beading, and even with welding toroidal insertions. You can set nozzle placement in different ways, including radial, hillside offset, tilt nozzles. You can set the position of the nozzle using polar or Cartesian coordinates. You can even use vector. You can also set some loads and defects, including, of course, pressure, including hydrostatic pressure, thermal strains, and you can set external loads from piping systems in different coordinate systems. You can just select which system is more convenient for you. Thermal strains, this is very important. Nozzle-FEM consider thermal expansion and correspondingly attendant strains, because, for example, your nozzle and shell materials can be different, can have different thermal expansion factors. So you will have some thermal strains and thermal stresses because of this. And here you see this, taking into account thermal strains will increase your stresses, for example, in this case, by 37%. Quite important. Load setting. There are two ways of load setting. You can set them on the edge and in junction. So edge is mostly useful when you have this type of nodes and you know your loads on flange. But quite often you have just welded nozzles, and how to apply and how to construct correct model and how to correctly apply this. This is known, for example, from ISME B31J document, that you need to set some appropriate load or length of the nozzle in order to take into account, to escape some edge effects and to take into account flexibility. So the software do it automatically. You can see here, for example, that depending of the length of the nose, you can have different picture. You can have some edge effects in your stress field. So ISME document prescribe us how to do this. And here is you see that if you will take a wrong length, you will have quite significant effect on allowable loads. So this is also done automatically. After you set all this data and settings, you just press the button and run the software. The software do everything automatically. It constructs the mesh and might run the solver. Here even can see the matrix of the system with all factorizations and so on, and produce reports. Usually this takes just several minutes. And after this, you can see the results in HTML report, which you can convert to RTF and to Word document. And you also can look at it. Let's look how it looks like. So this is how this report looks like. So you can see it's very similar if anybody of you ever use or deal with our PAS equip. It's just the same type of report. So you have sections, you can look at each section immediately. You will have some problems by red color and so on. And you have a lot of tables here, for example, tables of allowable loads. And here you see the copy button. And if you press the copy, you just get them into the, automatically get them into the clipboard and can insert this data in your PAS stress, PAS start prof, piping stress analysis software to check the loads. This is stiffness flexibility table. Again, you can do the same. You can just, with one click, just get this data, and by another click in Start Prof software, just insert this data as a data of your some non-standard piping support. And you have this kind of post-processor with which you can look at all details for your results, change view, make screenshots, and choose different load cases, and look at where you have the biggest stresses, and so on. And also, of course, displacements. So last but not least, a very important question of integration, because this software is on the boundary of pressure vessel design and piping design. So it needs to be integrated with appropriate analysis software. And it is. So if we have some pressure vessel in our PAS equip software, we can just generate corresponding files with all data for any nozzle shell junctions, and just open these files with Nozzle-FEM and immediately run it and get the results. And we also have PAS Start Prof integration, as I described you earlier, but we're going to improve it. And in the next version, it will have, first, it will have full model for WRC in our Start Prof. And second, we will have integration not via clipboard, but via direct integration between PAS Start Prof software and PAS Nozzle-FEM software. So you just, if you have from nozzles and for non-standard T, for example, in Start Prof, you can just press the button. And if you have Nozzle-FEM installed on your computer, Nozzle-FEM will start it, get all data, run the calculation, and return the data to Start Prof for piping analysis. Okay, some pictures with advances and some interesting models. Oh, okay, for example, this is how hydrostatic pressure is influenced. You can see different levels of stresses, because this is Here you have some models with flat surface, or this is, for example, for membrane trace, because of connections of skid and the vessel. Also, this is an interesting configuration. Here is a conical reducer with two nozzles, membrane with different membrane bending stresses of different combinations of stress components. Yeah, and you can also calculate connection between shell and supports. And we are going to add more and more useful typical geometry configurations in the future. I think that's all for the presentation.